For question 8, it says, protein kinase A has popped up in this class a time or two. Explain what activates and inhibits protein kinase A and what its activation and inhibition would cause. So starting off with the processes that protein kinase A is involved in that help us break down our fuels. The first is glycogenolysis, which is the breakdown of glycogen to help us then break that down further into glucose, and then have that glucose be sent off to glycolysis. So what happens is we're exercising, so we want to break down our fuels. So epinephrine, norepinephrine, glucagon, and growth hormone are released. That activates adenylate cyclase, which then tells ATP to convert to cyclic AMP, which activates protein kinase A. So cyclic AMP is one way that protein kinase A is activated. From there, glycogen phosphorylase kinase is converted to glycogen phosphorylase, and we have glycogen, which is converted to G1P, G6P, and then enters glycolysis. The other way that protein kinase A works in helping us break down our fuels is through lipolysis. So again, we start with these beginning steps. Cyclic AMP activates protein kinase A, which then goes on to activate the enzymes ATGL, HSL, and MAG, which will further go on through lipolysis to help us break down triglycerides to form free fatty acid long chains that can then be converted in beta oxidation to acetylcholine and sent to the Krebs cycle. So for the processes that are involved in helping us store our fuels, we have lipogenesis and glycogenesis. So with this, insulin is released, telling our body we need to start storing our fuels because we have excess fats or fatty acids or excess carbs, glucose in our blood. So we want to store that. So insulin's released, and that activates phosphodiesterase or PDE. PDE not only inhibits adenylate cyclase, but it also inhibits protein kinase A. When protein kinase A is inhibited, that means that we are not breaking down our fuels, but instead we are starting to store them. Another role that insulin plays is it activates PP1, which goes on to activate glycogen synthase, and glycogen synthase in glycogenesis inhibits protein kinase A in the same way that protein kinase A, when we're going through glycogenolysis, inhibits glycogen synthase. Glycogen synthase is, like the enzyme infers, we're synthesizing glycogen or we're producing glycogen. So when protein kinase A is active, we don't want to be doing that because we want to be breaking down our fuels, but when we want to be storing our fuels, then we want glycogen synthase to be going, so we want to inhibit protein kinase A to stop breaking down our fuels so we can start storing our fuels. Some other things included in this flow chart is calcium. When we have an increase in calcium, that means we're exercising, so we activate CAMKK, which also activates glycogen phosphorylase, and calcium activates glycogen phosphorylase kinase, which continues on with this process that protein kinase A has continued to activate. In the same way, we have an increase in ADP, increase in AMP that activates glycogen phosphorylase, and we activate AMPK, which also goes and activates these enzymes involved in lipolysis or the breaking down of our fats. In the same way, protein kinase A helps us activate lipolysis as well. So protein kinase A helps us in the ability for us to break down our fuels and is activated by cyclic AMP, and it goes on to activate these three hormones involved in lipolysis, and it goes on to activate glycogen phosphorylase kinase to help us go through glycogenolysis. And when protein kinase A is inhibited, that means we are storing our fuels through lipogenesis or glycogenesis. PDE inhibits protein kinase A as well as glycogen synthase, which are both activated through the release of insulin.